Good day, my name is John Azariah. I'm actually an Australian, but I work in Redmond. I work on the Microsoft research team, doing some work with the quantum computing group. And I do functional programming and F# for a day job. So I try to infect as many people as possible with this disease and get everybody to sort of look at things functionally and so on and so forth. One of the interesting things I've found is a set of tools that actually make it very easy to solve certain difficult problems. And in some sense, this talk is actually about that. We're going to cover 4 major questions. What are algebraic data types? Why do we care? Why do we need them? Okay, so now that you've convinced me, twisted my arm, that we need algebraic data types, what does it look like to have one in C#? And then how do we get C# to actually give us these types? Because it's one thing to write the thing down by hand. Can you do something better than that? And really that's the structure of the talk. You'll realize a little bit later on that there's a bit of bait and switch, but I won't tell you what it is right just yet. You'll have to stay awake and ask questions and stuff like that, that kind of thing. Too fast, too loud, too everything okay? Clear? Awesome. Who knows what algebraic data types are? Joe, of course. Who else? Cool. So we can start this with the appropriate kind of threat. I've threatened to hit you with type theory at 9 o'clock in the morning. But this is actually all the type theory you're going to need and all the type theory you're going to learn, what you're going to hear in the next 30 seconds or so. What is a type? A type, you can think of a type as a set of values. Okay, so you have a set which is just an unordered set of values. So now you have a set. How do you make a bigger set with 2 sets? Well, there are a couple of ways of putting those sets together to create bigger sets. So in some sense, the question really is, how do you create a bigger type out of a littler type? And the algebraic mechanism that we're going to talk about is really all there is to know about the type theory behind this. All right? Have I lost anyone already? No. Cool. So there are 2 ways of making bigger types out of smaller ones, at least 2. You can think of them as basically mathematical operators on top of sets. So think of one way of doing it is take every value in one set and every value in the other set and then just cross pair the 2, sort of like a cross join. And if you think about what happens there, the cardinality, the number of elements in this product set is actually the multiplicative product of the cardinalities of the individual sets. So if I have byte and character and I put two of them together, well, my composite type will have all the possible bytes multiplied by all the possible characters. That's the cardinality that I would get, right? And in some sense, we're very familiar with this because this is really the only sort of type composition stuff that C# and Java kind of encourage. It's basically structs of some kind. Another way of looking at it is to basically take all the values in the one type, tag them up with the name of the type, all the values with the other type, tag them up with the name of the type, and put them together in one set. Then you'll have a sum of the cardinalities of the constituent types. You guys with me so far? Turns out that's actually very useful to represent choice. And when you start doing domain modeling and stuff like that, with just product types, usually you'll end up having all kinds of convoluted mechanisms to try and limit the kind of limit the space of values to just valid ones. And so you'll end up having a whole ton of things that are composed in the type system but are actually invalid for use. And then you have to write a unit test to make sure that that invalid thing doesn't actually show up, or if it does, then you do the right thing. And in some sense, you lose the ability for the compiler to tell you, hey, you can't possibly create one of these things, and you push it down to a unit test kind of thing or a runtime check to figure out whether you've got something that makes sense or not. The other thing that we need to kind of be careful about is value semantics. Now, if you think about sets, sets are actually sets of values. But if you think of a Java class or a C# class, the cardinality of the type that takes an int and a string, for example. Well, a string is a bad idea, but an int and, say, a byte, right? And you create a class with those two properties. The cardinality of the set of those types is not related to the cardinality of the constituent types, because we can create references and pointers. So you can create 100 objects with the same int and the same byte, and the type system will think they're the same, but the runtime system will tell you that they're different because you're comparing references. And so it's important in our discussion here to talk about value semantics, and we're going to try and get values actually to be the primary way we think about types and sets and values and so on and so forth. So let's see. Hang on, what's going on here? There you go. So how many people here do like domain-driven development for a living? You know, build business applications, boring business applications? Yeah, me too. I used to do that. When you do modeling with a boring business application at the moment, so I was just talking to Joe a couple of minutes ago, we were talking about payments, right? What's a valid payment? Well, you can give me cash of some kind. You can give me a credit card. You can give me a check. Well, in the US, you can get a check. Nobody uses checks here anymore, do they? Right, no. So, but you can do a BPay or whatever it is, and you'll end up having different mechanisms for doing that. And each of those has a valid sort of adjoint value associated with it. So a check will be associated with a check number, a credit card associated with a credit card number. And the traditional way of actually modeling one of those things is to create this huge big record that you store in a database with a whole bunch of fields that are going to be null. And then somewhere along the line, you have to write a little piece of validation code that says, hey, hang on, make sure that at least the correct thing is here. So if it says that it's a credit card account, there better be a credit card number in there. And that level of validation makes it very difficult for us to reason about the code itself. How would it be if the type system didn't let you put in a check without a check number or a credit card without a credit card number and still treat the whole thing as a payment? And in some sense, that's really what algebraic data types kind of good for. They make it easy to represent the values that are valid and make it difficult to represent values that are illegal. And consequently, they do that at a compile time rather than at a runtime kind of check. So the type system in the compiler is actually going to support you to make sure that you're doing the right thing. And this is not whimsical. And this is probably the only time you'll hear me say this in the entire talk, but there's actually mathematics behind it. There is actually strong mathematical theory that equates or relates propositional logic and type logic. And it turns out that if you have a strong type system, you can actually make strong claims about when the compiler passes a program, whether it's actually correct or not. You can make certain claims about that. So algebraic data types are useful for that kind of thing. And now let's go and see what they look like in C#. So we looked at two different types. There's product types and, come on, give me the next slide. There's product types, and then there's sum types. So the way in which we do product types is very familiar. Everybody knows how to do this. Modulo the value semantics piece, right? Everybody knows how to build a record and a struct or whatever it is. That's kind of a product type. It's basically a tagged tuple. If you want to go with strict mathematics, you have a name associated with each of the fields, and that becomes, in effect, a product type. The thing about value semantics, though, that changes things because you can't modify anything anymore, right? Because if you say make something immutable, a struct of b comma 3 is always going to be b comma 3. It'll always be that. So if you want to change the struct, you have to actually have a new struct that has the appropriate value. If you want to make 3, 4, then you have to have a different struct that is b comma 4, a different value in the type system that needs to come out. And of course, that makes it kind of difficult to write because every time you want to do something, you've got to copy it and then set the thing. So the only time you can actually make a change in the state of the struct, the container, is at construction time. And so every time, imagine a struct with 40 different values in it. you've got to make sure that all the 40 different values are copied over. It's very brittle code. Every time someone adds a new property, you're going to be more trouble, right? And it just looks like you're about to shoot yourself in the foot. The way to get around it is to use a copy constructor. So effectively, we'll have some way of actually saying, here's a different constructor that allows me to set just 1 or 2 or 3 or 4 properties. And everything else that I say is actually from the source object and should automatically happen. Now, I'm going to show you what the code looks like, but let's just talk about the structure for the moment and just get an idea of what the code would look like. We'd create a sealed partial class because we don't believe in inheritance. Like there's no inheritance of values. What does it mean to inherit 3? It doesn't mean anything. Well, you can't inherit a tuple of 3 comma b. Well, so we'll create a sealed class. We'll make it partial though, because then we can do some interesting things with adding other behavior to the type. But as far as the type itself is concerned, we only need to have it as sealed. It'll have read-only properties because you want to be able to look at the individual fields inside the tuple. We need a constructor because the constructor is how you actually create the initial pairing in the first place. And then we talked about sort of vaguely about this width thing, which basically turns around and says, yeah, I have 15 properties. You can set any 2 of them or any 1 of them, whatever it is you want, and I'll copy the rest over from the original source that you have. And that should make it easier for us to do something functionally. And then there's value semantics, which makes sure that when you equate b comma 3 with another object that says b comma 3, they actually do turn out to be truly equal. So there are a couple of interfaces that .NET has to, that .NET asks you to provide. You need to override a couple of methods, and there's a bunch of boilerplate that needs to go in there to make value semantics work, right? Now, some types are damn sight more complicated, actually. What we'll end up doing is how do we normally model some types in the object-oriented world? Base class, bunch of derived children, some kind of runtime check to say which of the types of children you've got, and then you have, so how, payment. If you crack open a book on C# and ask how payment is actually implemented, there'll be an abstract base class called payment, and then there'll be a check payment which inherits from payment, and then there'll be a credit card payment which inherits from something else, and so on and so forth. And you'll end up having this mechanism where you treat something as a payment, but when you want to actually figure out what kind of payment it is, you've got to do some runtime type dispatching or runtime type checking to figure out whether you're dealing with a check or a credit card or whatever it is. There's a problem with that. What if I add a new type of payment? How does the compiler tell you that there's a whole ton of code there that's actually only trying to check against 3 different types when there's a 4th type that I've just added? You guys must be using ReSharper, so because you don't have this sense of horror on your face. But the reality is that in a very large system, or in a system that is only dependent on an open hierarchy, an open inheritance hierarchy, you're going to land up having this problem. And we don't want to have this problem. We want to have a closed hierarchy that basically doesn't allow you to add something without you knowing about it. You want every time something changes in the payment hierarchy, you want all the places where payment is used to actually turn around and say, yes, I know how to handle this new case. Or, oh, we don't have check payments anymore. I don't need to handle this new case. I don't need to handle this old case. So we do that by basically creating a closed inheritance hierarchy, and we make it opaque so that we don't actually allow anyone to see what the individual types are inside, because I don't want any runtime checking. Of course, once I do that, how in the world am I going to get the behavior that I want, which is going to be different for checks and different for credit cards and different for cash? How am I going to actually make that happen? Well, we use functional techniques for this. What we'll end up doing is we'll create a method called match, and we'll give a different lambda for each different case. And what that can do is delegate to the appropriate match implementation inside the class, and that can actually do the right thing. So as the structure of the code might actually look something like this. Let's, you'd have a private constructor with a sealed partial abstract class, so nobody can actually extend this class anymore. Nobody can actually instantiate the outer class. There's no concept of making a payment because you have to tell me what kind of payment you want. So there is a private constructor that prevents you from doing anything funny with the outer class. But I need to create one value constructor per type on the inside. So I'll have to have a check payment type of thing over there, or a cash payment type of thing over there. So the choice constructor would allow me to create an instance of an object. And the instance of the object would be one of those private sealed partial choice classes. So I created one class for every type of discriminant in the discriminated union, and be able to create an instance of those. So the only way you're going to get at one of those choice classes is through this constructor. And the only way you can actually get the choice class to do the right thing is to call the abstract match function and say, here are the four choices that I have, run the lambda against each of those, run the right lambda against each of those. And because that is abstract, and you have a concrete match function that overrides that abstract function, the right kind of payment will accept the call and call the right lambda with it. And so in some sense, you basically do a dynamic kind of dispatch, but you're doing it with static safety. So imagine what would happen if I create a new type of payment. Well, I would have to open sealed partial. I would have to open this class, add a new choice class inside it. And because I added a new choice class inside it, I would have to add a new argument to the abstract match function, fix all of the others to actually fix the right thing, fix all the call sites to say, hey, you now have a new type of payment that you have to deal with. What if I have a Bitcoin payment? Give me the lambda that I need to use in your case. And so the compiler will now step up to the game and say, I'm not going to let you go until you fix every one of these things. And a whole bunch of runtime problems go away. And in some sense, this is exactly how, of course, on top of that, you have value semantics, which is a constant now. This is, in fact, how most functional languages actually implemented. If you look at the inside of F# union, it'll look kind of like this. If you look at a Scala discriminated union, they explicitly tell you, hey, this is what I want you to do. Create me a trait and create me these three classes that actually inherit from this trait and close the hierarchy for me. And in some sense, this is kind of what we want. Now, I've wasted 18 minutes of your time blathering on about type theory. Why? Because really, the problem that we're trying to solve is this one. It's all well and good to understand how you create an algebraic data type with all of this boilerplate stuff. But we're humans, right? We're lazy. We are error prone. Who wants to be writing this kind of stuff? Do you? I don't. I don't want to write this kind of stuff. I want the language to give it to me. I mean, F# gives it to me. Why can't C# do it? Scala gives it to me. Why can't C# do it? So really now, what we're trying to do is step back a bit, and let's try to solve the real problem that we want to solve, right? What we really want to say is, I intend to have a discriminated union or an immutable record. I don't care about the implementation detail. I only want to tell you, hey, by the way, I have a choice class that is either maybe of something or none, because I don't want to have nulls in my code. All I want to do is represent that. And then I want to use some functional technique, some mathematically transformational technique to write the code for me. Because what are you going to do when you have to write the code? You're going to follow a recipe. What is a recipe? It's a program. What's good at running programs? Computers. So why don't we write a program that takes this intent declaration and generate the code? Does this sound familiar? You kind of do this all the time, don't you? This is what compilers do. This is exactly what compilers do. You don't talk about bits and bytes and moving things around. You talk about for loops, and you talk about maps, and you talk about link, the higher level abstractions. You want to extend the language the compiler of the language isn't giving you the support right now. What you want to do is extend the language somehow. And in some sense, this is the bait and switch part of the whole talk. I'm actually not going to talk about type theory at all. That was just a sneaky way of getting you into this room at 9 o'clock in the morning on the day after the party, right? Because the faithful will be here. The really sneaky thing that I'm doing, the real thing I want to talk about, is the approach of being able to create a domain-specific language, a little language to represent an abstract thought. Find a way to actually do the transformation into code, integrate it into some form of tooling that allows you to use this on a daily basis without having to actually tear your hair out by the roots and start writing tens of thousands of lines of code for all kinds of stuff. This approach, I have found, is actually very, very useful. I've written all kinds of stuff with it, including state machines running on Orleans and all kinds of other things. This is a very useful pattern. It's a very useful tool to have under your belt. So I'm going to spend the rest of the 40 minutes talking about how to go about doing that. The approach that you take, the tools you'll need, and how you can actually start experimenting. So if you're here looking for real hardcore type theory, it's the example, not the point of the talk, it's the example in the talk. Is that okay? Cool. Right. Scott Lashin comes up with really cool ways of saying things. He has a website called F# for Fun and Profit. Of course, we're going to now do DSLs for fun and profit, so I apologize to him. And these are the sort of concepts that you need in your mind in order to make this kind of thing work. So there's representation, right? We need to figure out what it is that we're trying to represent. We need a syntax. We probably need some semantics. We need to basically make sure that we understand what it is that we're representing in some sensible way, not arbitrary way. By the way, the arbitrary way is called a spec, and you give it to a developer, and then they sit and have discussions over it for several months. This is math. You're going to talk about it in precise, unambiguous terms, and there are tools for doing this, and we're going to talk about a couple of them, and we're going to talk about how we're actually going to implement some of this stuff. And this becomes unambiguous. And when you have unambiguous input, you can have reliable, predictable, deterministic output. And that's what that is. And the last bit we're going to talk about is, because we love Microsoft, I work for Microsoft, and we use Visual Studio because it is the best. We have a way of actually incorporating whatever tooling that we have in here right into Visual Studio, so you can have a completely seamless dev experience. Even though you cooked up the language on Tuesday and you whipped the whole thing up by Friday, people coming in on Monday morning won't have to change anything about the way they work. There's power in this, right? So let's actually talk about how we're going to go about doing this. So the first thing we need to do is figure out what idiomatic representation of your problem looks like, right? You can start by being simple. You can talk about, I would like, maybe, you draw the architects will draw the white box. Programmers will write some pseudocode of some kind. And really what you're saying is the pseudocode is in some sense idiomatic with what I want to represent, and it hides the detail underneath. Another way of doing about it is actually using proper semantics engineering. Now there is actually a whole slew, a whole spectrum of tools that you can use, starting on the one hand with simply expressing the grammar of what you're trying to do in EBNF or some fairly low-level tool, going all the way up to PLT Redx and actually building out an evaluation context-based semantic parser. You can do that. You don't need to go all the way to that side, but there's benefit in pushing things further to the right because you'll end up getting more and more structure in what you're doing. But the outcome of doing the semantics design is what is known as an abstract syntax tree. And that is effectively a type that tells you what a valid node in this tree that represents what you're going to represent, what a valid node looks like. And again, there it becomes fairly straightforward to actually use algebraic data types to represent the tree. So we'll use that in a sensible language. Let me show you what I mean by that. So can everybody see this? I'm going to show you the class maybe. Okay. Now I would like. Okay. Let's look notionally at this line right there. I'm really saying I'm going to define a type, which is a sum type. I'm going to call it maybe. It's a generic type of type T, and it has two choices. The value constructor of a constant called none, a singleton, a value constructor that takes a value of type T, and I'm going to tag it with sum. So remember that we had the two types that we talked about, and we're going to tag each of the types and then put it together. The cardinality of this is effectively the cardinality of T, because every T we're going to tag with sum, plus 1, which is this unit that tells you, hey, there's a value that is not of T, but it represents the absence of something. If I had to go through and do just this one line and go through the process of actually implementing the types that we talked about, the hierarchy and so on and so forth, this is what it would look like. There's your private constructor, there's your match function, there's the two value constructors, here's a container that holds the two choice types, here's what none looks like, here's the value semantics piece of none, which basically says if the other is none, then I'm equal to it. Otherwise, make sure that I am exactly the same as that, because I'm comparing two singletons. And here's the match function that basically takes two lambdas, one for none and one for sum. And in the case of none, it says call the one that I need to do for none, right? And then you do the same thing for sum in here. But here you need to store a value. And so the constructor is a bit complex. And then you do the same thing over here. And here's the value semantics for the top level thing that says, given two maybes, are they the same? Who wants to write this on a daily basis? I don't. Nobody wants to. The moment you start putting credit card payment and all of this other stuff, you've got to keep track of all of this thing, and it just becomes difficult to do. The pattern here is, like I said, safe, because it's sealed, opaque, partial class that just doesn't, you can't do anything funky with it. But to get this level of safety, you really want someone else to do the work for you. You want a machine to do the work for you. So this is an example of what syntax might look like, and this is idiomatic. If you saw this in C#9, you wouldn't bat an eyelid. It doesn't look like some other funky language. It just has a new union keyword, and all the things inside are basically separated by pipe. It's not entirely unreasonable. And the record type is exactly what you would expect from a struct. Right? Again, not unreasonable. So if I want to represent this little language now, I need an abstract syntax tree that represents it. So I need to have something which handles a namespace, which handles what a namespace name looks like, handles an arbitrary block of members in it. A union member looks like that, a record looks like that. They can be generic, non-generic. This method, this constructor in here could be generic or not. So it starts getting a little complicated. The moment you start sitting and thinking about this, it becomes a full-blown exercise in language design. So we represent the AST, and in about 50 lines of F#, because the AST is actually builds on top of things. Let's start at the bottom and work backwards. You've got a namespace which has a name, which is a kind of dotted name. Namespace members have a list of namespace member. A namespace member is one of these three types. A using has a dotted name associated with it. A record type has dot, and so on and so forth. Then you build the whole thing up all the way to the top, and you finally come up with, I know what a symbol is, and a symbol is just a bit of string. Right? So this is the most basic piece in this, and we're composing it all the way down, and we can build up an AST with it. Now if I create an object of type namespace, will I get a valid namespace? You bet I will. There is no concept of giving me a none, a using with a missing dotted name. You can't do that. It's just not possible to do it. Because if you say that the namespace has a namespace member and the namespace member is using, it better have a dotted name or method inside. And there's no way to construct one of these things in an invalid way. So now that you have this thing and you have this thing, you need to find a way to go from here to here. And this interesting piece of technology is called a parser. Now, I'm not going to go down and get into the nitty-gritties of how to use the parser. There's several very good references out there. Scott Lashin has one, Phil Trelford has one. fparsec, just go look for it. You'll find the nitty-gritty details of how to get into that. The purpose of this talk is to say, here's all the pieces that you need in order to make this big picture happen. So, and of course, I'll answer questions, but I'll give you an idea of what that looks like, right? So, parser combinator libraries like fparsec do a very succinct, beautifully clean job of actually representing pieces of code that transform text into AST nodes. And they look something like this. Which I will, where's my mouse? There you go. So if you think about this, forget about the prelude, which is there just to make the rest of it not look so red. But a symbol is basically an identifier that may be surrounded by spaces. That's what we define the symbol as when we create the AST. And this function called symbol now basically will take a stream of information, a stream of text, and return to you the first bit of it if it matches a symbol. Similarly, dotted name says, get me a bunch of identifiers separated by dots and make sure there's at least one of them, because a dotted identifier might actually come in useful somewhere. And we go all the way down, we have something that says, here's a list of symbols in the type argument. So for example, you have the type argument is very different from the type parameter list of an instantiation. So if you look at this thing, where is my mouse? For goodness sakes. If you look at this thing, you can only get type arguments over there. You can't put system.enumerable.list in there. You can't do that. It's a type argument on this side. So this better be a symbol. It should be a list of symbols, potentially. And that's what this says. So give me a type declaration is basically the type argument has a bunch of symbols separated by commas that have a point on either side of it. And then that should be followed by basically a symbol followed by optionally type args will give you a type declaration, and so on and so forth. So we go down to type reference, and then we figure out a whole bunch of things. And this is not quite 50 lines, but it's 100 lines of code, and it'll actually figure out how to handle all the way down to namespace. Again, the brevity of this should astonish you. It doesn't take much to actually do the heavy-duty work that we're talking about. The tools are there. There's just a whole slew of them that you just need to be aware of, and then the moment you have that under your belt, this becomes a valid alternative to actually hand coding a bunch of stuff. Right, how are we on time? 35 minutes, okay, sounds good. Tree rewriting. Now, I lied when I told you that the AST wouldn't represent invalid values. Somewhere along the line, you can pass in an empty string. Is it okay to have a namespace with an empty string as a name? Well, the symbol regex may give you an empty string. And what am I going to do with it? Well, I need to find some way of actually validating it. So in many cases, when you're starting to write more serious languages, in many cases, you'll take the AST that came from the parser, which would have actually gone through a whole bunch of syntactic syntactic checking. And if you add a symbol table to it, you can actually do type checking type of stuff. So you can build a C parser if you want using this mechanism, right? And have a symbol table and pass it around. Make sure that you're only referring to things you've already declared and all that kind of stuff. But at the end of the day, you may have some semantic rules that you need to apply. So usually there's a second pass in this whole thing where you're given a tree and you write a visitor pattern kind of thing that takes that tree and returns another tree. And the result tree may have nodes missing in it because you've removed them, or it may have nodes injected in it, or you may replace a given node with two other nodes, or whatever it is that you want to do. the rewriting portion of this is actually one of the phases in this whole sequence. Now, because we're writing the stuff in F#, we have some interesting ways of composing these building blocks. I will use the word monad only once, just because I have a reputation for being, I have the propensity to use it evidently, so I'm going to keep the reputation alive. So I did say monadic composition of these individual blocks, and that's actually how you glue the pieces together. So you have a parser that gives you a monadic value of an AST, and then you have rewriters that take monadic values of the AST and then give you more of those, until at the end of the day you've come up to the last stage. Now, how many of you have used Roslyn before? Joe, of course. And okay, so we have one other person, so brave person who's actually used Roslyn. Have you used CodeDOM? Has anyone used CodeDOM back in the day? Okay, so Roslyn is basically Microsoft Compiler Services. It has a full-blown parser for C# and so on and so forth in the front. It also has a code generation piece, which is very similar to CodeDOM. It effectively replaces CodeDOM. So how do you think Roslyn works? Well, Roslyn has its own AST, right? It's got text, it's going to take it, it's going to look like C#, the text looks like C#, it's going to create an AST that looks like the meaning of the C# program. It's going to do a whole bunch of rewriting there, so all your refactorings and all the other stuff that can happen in the AST rewrite. And then they take that AST and they actually generate C# code with it. Roslyn already knows how to do that if you give it an AST that is valid. Now, we want to actually cheat Roslyn now. We say, yeah, I'll give you a valid AST. I'll give you a valid Roslyn AST. You go off and do the code generation for me. And so the last transformation that you do is write a transformer that takes your AST instance and converts it into a Roslyn AST instance. And then you let Roslyn deal with the rest of it. And that's kind of how we do this stuff. But that's actually kind of, how do you say, easier said than done. Let me show you what the Roslyn AST looks like. So I'm going to, again, cheat. I want you to pay close attention to this class. So starting at line 23 and going down to line 39. Pay close attention to that. Because the tree I'm about to show you is only for that class. Not for the whole thing, just this bit, right? There's a handy tool out there that actually allows you to generate the Roslyn equivalent of one of these things. And it actually buffs if you give it the whole class. So I'm just asking you to look at this. So it's got a constructor with an argument. It sets a property, there's a private property, there's a match function, there's a bunch of overrides that you have there. I'm asking you to not even bother with, just ignore, let's look at just that class. If I did that, you see that thing over there? You're looking at that bit. This is what the Roslyn AST looks like. Anyone think that it's easier to write the boilerplate code than the Roslyn AST? Because I actually think that, right? You just shot yourself in the foot by saying, I'm going to build this thing, and this thing is not even human readable. I can at least write the boilerplate code and look at it and have somebody code review it and make sure that it's actually doing the right thing. Anyone want to code review this? Right. So how are we going to create this thing from the AST that we had? We had a nice clean AST that said, here's a namespace, and it's got a union type, and it's got the union type has a union type member of something that takes the argument t. And just that one node is going to generate this kind of thing. How am I going to actually get this piece out? And the answer to that is another DSL that we cleverly wrote a long time ago using sort of F# black magic. Okay? Now F# allows you to write functions that have any number of arguments, and you don't have this ceremony of putting brackets and commas and things like that inside. So because everything in F# is just an implicit list of arguments, and you can call things whatever you want, we can actually create complex looking functions with very complex arguments and make them look like the code we want to generate. I'll give you an idea of what I'm talking about here. So I could write a function called class that looks like that, which takes one argument called class name, followed by some white noise argument which I'm never going to use, followed by a list of potentially type arguments, another white noise colon, and then something that tells you what the base class is, and then a list of interfaces that I implement, followed by a list of modifiers, followed by something that looks like a block. And in that block, I will give you each of the statements that I want to put inside. Now, if you looked at this code, it kind of looks like what we want. We want to create a class, right? I mean, this is what we want to create. We want to create this class right here. We want to create a public partial class sum colon maybe t. So class, this would be maybe of t, and then it has a base class, which is the other, the maybe of t, and it's a public partial class, and it's got a constructor inside it, which has the same kind of principle behind it, and it has an override for equals, which has an arrow method, so you put a fat arrow in there and put an equality expression, so on and so forth. This is much easier to write than it is to actually compose the AST from the transform. And this library is available on GitHub, so you can now go and get this library down, and it's got its funky set of functions in there, and you can go off and actually write the code that looks like that. I'm going to switch to Visual Studio now, and I'm going to show you how the real code actually looks. And have I lost anyone?
Can you explain that? Once you've got symbols,
yeah.
Get a symbol next to a string. What structure is the F# stuff got?
I'll give you a second. Give me half a tick, and I'll show you the exact code. Right. Right. So it's a good question. So the question that you asked was, what does the structure of that function look like, and why would I use it? So in some sense, this is what I'm talking about. So here's our AST. Here's the parser that I showed you, right? And this time, it's all compiling, so it's doing the right thing. And here is the declaration builder for the union type class. And in this case, what I'm actually doing is I'm going to turn around and say, hey, given a union type member, I want to create the constructor from it. Right? The union type member will give me a name, the member name of the type. And that's going to be useful. If the union type member has a type, then I'm going to put a set of arguments that says I need to have an argument named value of that type. Otherwise, I don't. So if I go back to looking at this thing, we look at both the cases here. There's none and some. In this case, we don't even have to create a constructor because it's a singleton. In the other case, we want to put a constructor in there as long as there's a type argument. And in some sense, that's what this is. So. But what does this look like? This basically says, hey, I'm going to create a tuple. That looks like a tuple to you, right? And it's got to have these two things in it, which is the name of the variable and its type. So as soon as I create a tuple, it knows that that's going to be the value that I want outside. And what is the statement inside is basically, please set the value property, the big value identifier, with a little identifier value, and this funky looking operator is effectively the assignment inside our second DSL. So we're using the F# DSL, the Roslyn DSL, to allow us to create expressions in a nice clean way so that we don't have to deal with Roslyn at all. All the Roslyn member declaration garbage that you need to put in from this piece all of these member access expressions and the with expression body and so on and so forth, all of these things which form part of the Roslyn language that creates the Roslyn AST for you is actually hidden away inside things like this. So this DSL is actually available. As I said, it's available on GitHub. So it now means that you can write code that looks like this. So here's given my thing, here's what the constructor looks like. I have the assignments set up, and that's based on whether I had a type constructor or not. And then in the same way, I have a value property that only does something when you have so here's I either get a singleton or a value, and then I have a type reference to tell me, hey, that's a value of that type, or just a singleton value. Similarly, the match function override does the right thing. So all of this starts to look similar to the code that you want to write in the first place, and you can test each piece individually. And then it'll generate a piece of string that looks like the thing that you want, and you can make sure that, hey, okay, it's matching what I want, and that passes my unit test, so I'm now generating the right thing, compose the right set of builders into this game, if you like. And then all of a sudden you have this concept of the top level function taking a whole bunch of these creators to give you this. So make sure that I have the base value set up, make sure I have private constructor, match function, extract, the access members themselves, any wrapper type that you need inside, the equatable equals, so on and so forth. Each of these things is now a method, and that goes into this thing. So I take class name, and then inside that you have the members. So this is a lot cleaner in terms of being able to build up the structure of the thing that you want to code generate, rather than having to navigate through the Roslyn monk. Somebody else has already done the same thing for you already in that library, so you can use that and get this thing done. Right, so how are we doing on time? 47. Okay, right, so does everybody see how you can actually generate the Roslyn AST from this thing using these transforms? Because in effect, this is the last pile of transforms that take your AST, which is of this kind. So I'll show you, hang on. So this thing basically takes a union type and gives me a member declaration syntax, right? And these are individually composable. So rather than get this huge morass of things that you had in the past to get this whole tree and then do tree splicing and all kinds of other stuff, you actually build the thing up from the inside out by actually using this functional composition mechanism. And you'll create a bunch of these functions. So this one goes from union type to member declaration. There'll be another one that does records. There's the namespace itself, which if you think about it, has, I want to put in some warnings. I want to use the usings in there to make sure that the right things are used. So because I might actually reference a dotted type in the class, I want to have a using line put in there. So that's going to get generated correctly. And then you have namespace unapply, and then you have this thing. So it turns out that it's actually fairly easy to start putting these things together because you're building them up piece by piece and then composing them into larger and larger blocks. But at the top level, you'll end up getting something that turns around and says, give me one of the namespace, which is your AST on the left, and I will give you back a namespace declaration syntax, which is the Roslyn AST on the right. And then you can take that and give it to Roslyn and say, here's a valid tree, go off and generate code for it. And it'll do that. So that's what the code generator does, actually. So it basically does this. So given a file, open the input file, open the output file, read all the text, parse the namespace from the text, and then go from that namespace to a declaration, and then write all the output into the output, and you're done. So in effect, we've built a little compiler for a little language using all the various stages of a proper compiler. And you can build an executable out of this, which you can run on the command line. But who wants to do that? Nobody wants to do that. Let me actually come back to that in 1 second. Actually, let me see. Oh, I want to go back. So Visual Studio now gives us a very cool set of extension mechanisms for doing this. Has anyone here programmed in ASP.NET? WPF, right? So you guys know the idea of the code behind file, right? What is that code behind file? That code behind file is the code representation of the intent that you declared in whatever markup that you had up in front, right? Why is that any different from what I did just now? I created some intent in this union thing. Why can't I have a code behind file that actually has the same code and stick it at the back? And then I'm done. I can generate breakpoints and all kinds of other stuff. Look at the code. So it turns out there's a very cool way of doing this. You take this, instead of creating an executable like I showed you, you create what is known as a single file generator. Now this stuff is a little bit of black magic because it's not well documented, but it's roughly been the same in terms of its ethos since 2003. It's the only place I still use COM in Microsoft in 2017. Right? It has not changed at all. There is actually a place where you do a query interface for an interface, and then you do a Marshall dot analyc or whatever free on it. So the single file generator approach and the VSIX packaging is a little bit of black magic, and I'm happy to show you the code that does it. It's extraordinarily simple. You can literally take the code that's in my project and replace it with the function that you have. And what it is every time you save the top level file, it calls the tool, gives it a bunch of text, and then expects to get a bunch of text back. And if anyone attended Joe's talk yesterday about how to get two processes to actually share memory, it actually uses shared memory to do precisely that. That's exactly what it does. So it's a very old-fashioned COM inter-process communication kind of mechanism, but it works. It works beautifully. It has worked since 2003, continues to work today. You can provide even language support like code coloring and so on and so forth, which I won't get into right now. And if you actually generate enough information while you generate your C# code, you can actually put breakpoints. Now in our case, we're only defining a type, so there's nothing to really put a breakpoint on. But you can quite easily see that if you were representing sequences of operations, you might want to step through the top level language rather than stepping through the back end of it, and you can actually do that very straightforward way of doing it through this mechanism, both of which I'm not going to talk about right now. So let me, how are we doing on time? 10 minutes? Excellent. Right, what was I doing? I was going to show you some, I was going to show you the VSIX code. In the VSIX code, this is what the code generator looks like. It is ugly as sin. It might have been less ugly if I had done it with F#, but then again, you would have, this should horrify you, and that is the intent. Let's just put it that way. So you have COM visible true. You have to create for yourself a new GUID, and you have to register yourself a different type for the generator, and it has to implement IVS single file generator. And what it does, I did not lie. We actually do get IUnknown for object and query interface and release. Yep. But here's the magic. You get the byte string that gives you the input on the input. It gives you a string, and you generate code for the text, and it generates code which you then put into a byte array and send back. And you co-alloc to make sure that you've sent some shared memory back and forth. Literally, the only thing you will change is the entire file when you create your own little language is this one line or this one word. That's it. So everything in here, the black magic's been sorted out for you. Just change that one function and you're done. You can, it's text in, text out, and it'll make sure that the generated file is put out. And then they have a funny way of actually making this code thing available to anyone who wants it. You have to create a VSIX project and go through some mumbo jumbo to do that. Again, there's references out there that allow you to package the thing properly. And then you will get sent off to go and put things on Visual Studio Marketplace. So let me see. To actually do that? No. I think I killed the browser. But there's a Visual Studio Marketplace that you can actually publish your stuff on. And that'll come up, and you can, I'll show you how to do that. So there's a little bit of extra little effort you have to put, but it ultimately turns around and gives you a very nice experience, developer experience. I'm going to show you the developer experience. I'm sorry for fumbling around like this, but I'm losing my mouse. I'm so used to not having. So I'm going to take a look at this. I'm going to look at the test classes here. And I'm going to take a look at this reference class. You see here? And I've created this maybe CS union thing, which has a bunch of union types in there. And I'm going to remove the code generator. Right? And what this can, when you're in a C# project and you create one of these files, you can associate it with a custom tool. And this is that custom tool that you registered in the COM database. And when you install a package, you'll go in here to the extensions. And in the Visual Studio extensions, you can actually get it from the Visual Studio marketplace. So the whole process is a little bit convoluted, but this is how we package it for everybody to use. You write this tool, you put it into VSIX, you upload the VSIX to the marketplace, and then use extensions updates to pull the thing back down. And now it's available to everyone. The dev experience is easier, but this is how you actually publish the thing out. And then you have this union thing, which I've created, and it has documentation and so on and so forth. And once you do that, this becomes available. The custom tool interface becomes available. You can stick that in here. And let's say that I go off and actually just make a change and save the file, and voila, it creates the code behind for you. And this code behind should look familiar. This is exactly the code behind we had before. And now, because it's partial, you can actually create add adjuncts to it and do all kinds of cool stuff. So if you want to actually figure out, if you want someone to tell you, if you want me to tell you how to turn this maybe type into a functor or into a monad, I'm happy to show you. In fact, you can actually get it so that you can do link-based syntax on that maybe now. It's very trivial to do it because I generate a partial and then write another piece of partial code, and I'm done. So it's a very powerful way of actually building extensible code, and this is how it works. All right? So I'm going to summarize now on what are the steps that you need. Looks like a long list. Design the semantics. You need to basically make sure that you have the language grammar sorted out properly. Think about the edge cases. Try and use powerful tools. They'll help you. And then once you do that, make sure you get the AST that is equivalent to that. Design reasonable syntax, which actually gives you the AST once you parse it. Write a parser for it. Validate the thing using some tree rewriting stuff. Write the code generator to convert your AST into a Roslyn AST. And then set it up so that you invoke the Roslyn code generator and put the Visual Studio plumbing in there. And package the whole thing into V6 and Bob's your uncle. You're done. So you've now extended C#. Now anyone who uses this effectively extends C# to have union types and product types without any change in the developer experience. So instead of creating the 300 lines of boilerplate, you write the one line of top level code. Someone does the generation for you, and it's all idiomatic C# after that. So you're not doing anything funky. There's no background like binary generation, all kinds of stuff. You can go back and put breakpoints, look at the code, satisfy yourself that this is what it's doing. So in terms of actually even bringing the concept of union types itself into the language for you to use as a first generation type of thing, the key takeaways for C# programmers is effectively this. Use ADTs. They'll make your life easier, right? And it's a good thing, right? Using this mechanism, you don't really have to even make life difficult for anyone. Functional programmers, think about the idea of writing a domain-specific language when you want to abstract your problem up to the level where you only need to talk about the intent, not the implementation. So the moment you lift the abstraction level to the point where you can talk about it sensibly, there's a whole ton of mathematics that you can lean on that does the transformations that you can actually generate the code. So favor machine-written code over human-written code, favor a higher level of abstraction, and there are tools that are freely available. The parser combinator library is available, the code generator is available, and you basically can use that to do good stuff. And sometimes you have to show the C# programmers what they're missing. So you got to get them across and say, this stuff worked for me, and it made my life easier. So it's good to learn it, kind of thing. I think I'm done. I want to acknowledge Scott, who basically has been extraordinarily influential in giving us new concepts and stuff like that, making it available for everybody to use. A couple of guys, 3 guys from New Zealand and the US and Australia who have helped me with the functional side of things. And then Microsoft, who I work for, who has sponsored my coming here. So thank you very much. I will take questions for the next 5 minutes. All the stuff is available on GitHub. The VSIX is available on the workplace. And yeah, if you have a problem with any of the code I've written and you think you can do better, which I think you should, give me a pull request and I will happily accept it. Thank you. Joe.
You solve that by effectively with CodeGen create the sometimes.
Yes.
But the other, much simpler way, not quite as good, but the obvious simple way is to use generics. So you could create a generic type called sum of T1, T2, override the get equals, get hash code on that, and write a match method on that one.
Yeah. So like I said, the type theory part was the example, not the point of the talk, right? You are right in that you can do you can use generics to do that. The issue will end up becoming when you have none and sum of t. How do you represent the thing that doesn't have a value? And in some cases like that, you'll end up having okay, payment delinquent versus credit card partial versus credit card full. You don't know. There's probably one discriminant in there that doesn't take a value. How do you represent that? And there are also places where you'll end up taking more composite types inside and so on and so forth. So you'll end up having tuples of tuples and things like that. So yeah, I mean, there's ways to solve the union type problem. I picked this because this is actually the canonical way of doing it in Scala and F#. And it turns out that once you put the syntax in place, the syntax is favorably terse in C#. It's actually more terse in C# than it is in F#, because you don't create sum of t, you just say sum of t and you're done. So yeah, you have a valid point. You can do your type theory stuff however you feel like to solve the problem at hand. But really the point of the talk was to actually talk about using a bigger set of guns that you can bring to the problem to talk in a more abstract way. Anyone else? Cool. Thank you.